So this is the Stieltjes identity. All right. And this is from 1887. And what does it say? That says, if I have C of n is equal to sum of A, K, B, M, where K times M is N. All right. Now, if this one converges, sum of A, N converges, and if Bn is finite, then sum of Cn converges to the product sum of An and sum of Bn. Okay, have you seen this theorem somewhere? In some course, you've seen this theorem, then we won't have to do it. So, so you're saved. So we get this, and now here we are going to use the Stieltjes identity. Okay, so this one, so by what can I say? I can say that this one converges. Where does it converge? For sigma greater than half and tau different from chi different from chi naught. All right. Repeat. If chi is equal to chi naught, yes. Ah, you mean these are reversed? I've written something. So this, is this right? Yeah. And I wrote that somewhere before. So there was something wrong in my copying and pasting. And so, okay. So, yeah. So this part, I leave it to you as an exercise. Okay. I mean, we can do it. You want to stop? Are you tired? Okay. Because I did only easy things. You see, I had a bad conscience last week. Friday, I thought that I had done things which people were. So this one, all of this is easy to see, but should be seen once. Once in your life, you should do everything. Yeah, everything. You should do it once to be sure, so that afterwards you can use it. But be convinced. I mean, it's not because somebody says something that it's true. Yeah. So, yeah. What should we do? Should we continue? Do you want a break? Do you? What do you want? We continue? I mean, I don't insist on anything. If you want a break, we can have a break. If you want a break. Huh? No? Okay. So let's go on. Go ahead. Okay. So you know this. If I have A and Q to be co-prime, we know this, yeah? I'm writing it again, but you know it already. You know what? You know that I wrote it at the beginning of the class, chi bar A, chi of n, normalized by 1 by phi q, yeah? Sum this over chi, and this is 1 or 0. This is 1 or 0, depending on whether n is congruent to A mod q or not. You know this. So now if I go back here and I take my lambda, if I take lambda n to the power n power s divided by n power s, then what happens? So, and with the congruence condition, let's use this stuff, okay? Here, this one. So lambda n von Mongold to the power n by s with the congruence condition, n going from 1 to infinity, and n being congruent to A modulo q. So this will be equal to 1 by phi q, yeah, lambda n power s, n going from 1 to infinity, and the sum of chi, yeah, with chi bar n what is it? It's chi bar A, chi of n. All right. So this is equal to minus 1 upon phi q, and then use your sum of chi bar A, L prime by L S of chi. Okay. Let me give this a number. Okay. And this is true for sigma greater than 1. Okay. Now you know that Ls chi 0 here has a simple pole at s equal to 1. Okay. You know that by the part A. You know that part A, first part. Ls chi 0 has a simple pole at s equal to 1. So therefore, if I take L prime by L S chi, this will also have a simple pole at s equal to 1. And the residue is going to be phi, is going to be minus 1. You agree with me? So now, here I am. Here, what happens if S tends to 1? What happens when S tends to 1? As S tends to 1 but remains larger than 1, then what do you get? What about the right hand side here? What does this, what does this tend to here? This last one, this tends to 1 by phi q. As s goes to 1, this becomes s minus 1, and then an error term. Yeah? The right hand side of that equation, which is being called something of 2, is 1 by phi q s minus 1 plus an error term of 1. This error term depends on the q. Okay, so 2, let's call this 2b. All right. So ls chi, this is analytic for sigma greater than 0. So L prime by ls chi is also analytic except for the zeros of ls chi. Yeah. So L prime by L S chi is analytic every, except for zeros of ls chi. Okay, so now if you take the limit, so limit of s going to 1 but being greater than 1, L prime by L of S chi, what is this going to be? This is going to be L prime by L of 1 chi. Yeah? Chi is not equal to chi 0. Is there anything else that should not happen? Something fundamental that should not happen? Yeah, that requires more. L1 chi must not be 0. Yeah. So L and L1 chi is different from 0. Okay. If this happens, and if, yeah, I don't know if this is true or not. That's where Dirichlet's, that's what Dirichlet's big contribution was, to show this non-vanishing. L1 chi is not 0. Yeah. So so if chi is different from chi 0, and I use everything that I know till now, let me give this a number. So I have these 3 things here. Where are my 3 things? Here. I have expressed this in terms of here. I have got a limit, and I have written this down here. So if I take these 3 things into consideration, what happens? So if, so there's a big if, okay, if this is true, nobody said it is, not yet. It is, but we don't know it yet. Okay, so now if I know this, what can I do from here? So So let chi not be equal to chi 0. Okay, and let A and Q be co-prime. That's of course necessary. So from these three relations, what do I get? From 2, 2 which has gone, no, it's still there. 2 is there, 2b is here, and 3 is here. From 2, 2b, and 3, I can say that, what can I say? Sum of here, lambda n by n power s n varying from 1 to infinity, but being co-prime to A mod Q. This is equal to 1 upon phi s here, 1 upon phi q into s minus 1 plus O q of 1 as s tends towards 1. Okay. Therefore, lambda n by n n going from 1 to infinity, n congruent to A modulo Q. What should this be? What is this equal to? What is this? You see, this is going to, if, yeah, this goes to infinity. Okay? This goes to infinity. Is that clear for everybody? This goes to infinity. Now you take the prime powers, and what happens? So taking the prime powers, because lambda n, you remember the definition of lambda n is log power p if n is p to the power k and 0 else. Yeah. So now when you have the prime powers, sum of log of p by, this is when n is equal to p power k, log p by p power k, just the definition of lambda n, k greater than or equal to 2, okay, and p power k congruent to A modulo Q. This now is less than or equal to sum of, you can bound it by log of p and 1 upon p to the power k, all right, k going from 2 to infinity. You separate this out. This is overall p. This is equal to sum of log p, p into p minus 1, and this is less than infinity. Yes. Yeah? Yes. Yeah. Right, okay. From the above. Okay. So, so this shows that. So what can I conclude? My conclusion is, so as a corollary, if this condition is true, then I can say that this is Dirichlet's result. So What is the conclusion that I'm going to draw now? It is a corollary of infinitely many primes P congruent to A modulo Q. What remains to be shown is that L1 chi is not. Yeah? Log P by P minus 1, K is equal to Are you convinced? There will be, if we can, we still have some more things to show. Is it okay? Are things going all right for you? You are happy? Okay. I will just use one or two more words. Yeah, my dictionary is going to give you one or two more words. And then I will prove this stuff, which has been removed, but L1 chi is not equal to 1. To prove that, just some notation or definition, if you like. So you have all this. Is it okay? Okay, maybe we can remove this. And then we are going to find another way of writing the characters. The characters can be real or complex. Characters could be real or complex, yeah? So when is a character real? So definition, a character chi is called real, okay, if chi of n is real, but chi of n is then either 0 or plus 1 or minus 1. So if chi of n is either 0, 1 or minus 1. It is called complex, otherwise it is called, so this will be used in what will follow, and it's called quadratic. A character is called quadratic. This is called quadratic. When is it called quadratic? Of course, when it is quadratic, which means if chi square is equal to chi 0, yeah, but chi is not equal to chi 0, yeah. So a quadratic character is, of course, real, okay. A quadratic character is real. Quadratic character is real, but a real character, you agree that a quadratic character therefore has to be real, but a real character, it may be either principal or a real character. So either it is principal or the other option is or it is quadratic. So the proof of this statement, the proof of the theorem that chi of chi does not vanish at 1, this is going to use this bifurcation of bifurcation dichotomy, maybe, if you like. Yeah. So now I want to prove this. Yeah. So these words are introduced just to prove this. Okay. So either non-vanishing. Yeah. Okay. Proof. So we are going to separate this into two cases. So the first case is case 1, when chi is complex. Let chi be complex. What happens when chi is complex? There was formula which was written on the board, which I'm writing again. So we saw that. What did we see? We saw that LS chi is equal to, now I'm going to take the product of this. So sum of chi, sum of n going from 2 to infinity, lambda n by log n, chi n power s. And if I take the product here, then over chi, then this is an exponential. Okay, we saw this. And this is true for sigma greater than 1. All right. We also saw that we can take the sum of chi of n for overall chi, and this is either equal to phi q or equal to 0. I'm just repeating something that has been removed from the board. N is congruent to 1 modulo q, and this is otherwise. So now you want your product of LS chi, overall chi. And what you get, put this back over there. So using these two facts, so LS product of LS chi will become the exponential of phi of q, sum of chi n, yeah, this one. So hence product of LS chi taken over chi, okay, this is exponential phi of q, okay, and then you have a sum, the rest of what remains. What remains? Okay. So what remains here? Tell me. You have lambda n, you have n power s, and you have log n. Yeah. sum of lambda n power s log n. Is my log n in the right place? It is. Yeah, n is going from 2 to infinity. N is congruent to 1 modulo q. Now, if sigma s is equal to s is equal to sigma, okay, which is greater than 1, we get all these values are going to be non-negative and real. Therefore, L sigma chi product over, so S is being replaced by sigma, which is greater than 1, over all pi. This is greater than or equal to 1. Yeah? Because all of them are positive. Now you know that L S chi 0 has a simple pole at S equal to 1. Do we know this? I hope so. At S equal to 1. Otherwise, Ls chi, and if not, Ls chi is analytic at S equal to 1. So what can I conclude from here? Is analytic at S equal to 1. So what is the conclusion that I can get from here? So you see, you have L sigma chi is greater than or equal to 1. Yeah. So L 1 chi, this can be 0 only maximum once. Okay, it can be 0 at most once. Otherwise, what will happen to this? This one. This is the crucial expression that we have. This is equal to, this should have been, I don't know, my equation numbers have gone away somewhere. Let's give it some number. Let's not give it any number. It's just a green star. Okay, so here what will happen if there is more than one place where L1 sigma is L1 chi is 0, then this will tend to 0. Yeah, then this will tend to 0 as sigma tends to 1. Okay, so from here I can notice that L1 chi is equal to 0 can hold at most once. Okay, for if not, this one, my green star, yeah, this will go to 0. This will go to 0. This will go to 0. Yeah, when sigma goes to. So now one thing that you have not, have you noticed? Have you noticed the fact that I have not used the fact that chi is complex? I have to use it somewhere. Yeah, chi cannot, if we are making a case-by-case separation and I'm asking chi to be complex, then chi better be complex. I mean, somewhere it has to be used. Yeah, so if chi is complex, what does chi do when it is complex? It is equal to, it's not equal to its conjugate. Yeah, and both of them, chi and chi bar, are characters modulo q. Okay, chi is already a character modulo q. Yeah, if chi is. All right. So if I take this L as chi, okay, if I take its conjugate, then this is equal to L S bar chi bar. I suppose you know this. This is the Schwartz reflection formula. Um, so this is absolutely wonderful. L1 chi bar is 0 if L1 chi is 0. So if this is 0, then this is 0. This is impossible. Yeah. Hence, L1 chi is not 0 for chi complex. Are you convinced? Completely? Yes. Which two? Here. This one, this one, this one. Yeah. Why is it at most once? Yeah, because if you're if this happens more than once, okay, and if you come close to 1, then what will happen? If it is either it will never happen, or if can it happen several times that L1 chi is equal to 0? What will happen if L1 chi is 0 several times here? Then this will not be greater than or equal to 1. But we have shown that it is greater than or equal to 1. So you cannot have that. All right. So this is 0. Now, can I finish the last part of this? And then that's not very long. Then we can break, and then so at least you would have seen one nice proof in this one nice proof completely. Okay. So case 2, chi has become now chi is complex is done. Okay. So what is chi now? If chi is not complex, what is chi? If chi is not complex, what is chi? Is quadratic. Okay, chi is quadratic. Chi is quadratic. Okay. Case 2, chi is quadratic. So now I will do something quite simple. I'll take a Dirichlet series, R of n, and this is equal to sum of chi of d for d dividing n. Okay, this is a function, and construct a series R of n by n power s. Take the sum, n going from 1 to infinity. What does this become? This becomes, what do I pull out from here? I can pull out a zeta, okay? Zeta of s, okay? And what remains is L s chi for sigma greater than 1, all right? So this R of n, you can work it out exactly. No big mystery in this story, okay? What is this R of n? R of n is multiplicative. So if it is multiplicative, it is enough to know the value of this function at prime powers. And help me please find its values. It's R of, so at prime powers means R of p to the power alpha. Okay. r of p to the power alpha. What can r of p to the power alpha be? R of p to the power alpha, I can exactly work it out, prime power alpha. So if p divides q, what is it equal to? If p divides q, this is equal to 1. Yeah. So, okay. And if chi of p is equal to 1, chi at the prime place is equal to 1, yeah, then this is equal to alpha plus 1. And so chi of p can be 1 or minus 1, yeah. So if chi of p is equal to minus 1 and and alpha is divisible by 2, what is this? It's equal to, look at this, r of n. What will r of n be? Sum of chi of d divides n. If chi of p is minus 1 and alpha is even, then this will become 1. Okay. And the last case is if chi of p is minus 1. So I have chi of p1, chi of p minus 1, and here 2 does not divide alpha. Okay. So in this case, what is it? Good. 0. So I don't really care. I mean, what I want to show is that it's positive. I didn't have to work on this out. But just to convince you, so r of n, since at prime powers it is always greater than or equal to 0, so r of n is greater than or equal to 0, yeah, for all n. And r of n square is greater than or equal to 1 for all n. You agree? It's greater than or equal to 1. What happens now? So now I will do something by contradiction. So assume that L1 chi is 0. So now we assume that and we show a contradiction. Now, what do you know? You know that. What do you know about zeta s Lx chi? This is analytic for sigma greater than 0. Okay? This zeta s Ls chi is analytic, yeah? For sigma greater than 0. And then I'm going to use Landau's theorem, which I hope you know. If you don't, we can do it as an exercise, which, I mean, Landau has many theorems. So what do I mean by Landau's theorem? Sum of r of n power s converges for sigma greater than 0. Do you realize which theorem I'm using of Landau's? So this is the theorem that I'm using. So, okay, we believe that Rn square and all that are true. So Landau's theorem tells us, if you haven't, what does it say? This is a theorem of Dirichlet series. It says that if I have alpha of s is equal to sum of an n to the power s, with finite as its abscissa of convergence, so you are taking some Dirichlet series, then abscissa of convergence, and if all the ANs are positive or at most 0, then sigma C, which is the abscissa of convergence, is a singularity of alpha S. Have you seen this theorem already in a complex analysis course or something? We can do it. These theorems don't require a lot of skills lot of tools. Skills, yes, tools, no. So we can do them, yeah? So this is an exercise, yeah? We will do that. So we use this. Now if you use it here, what happens? I have zeta S Ls chi, yeah? So, and R of n is that. So using Landau's theorem, what do we get? We get that sum of R of n power s is, it converges for sigma greater than 0. Now comes the contradiction. So sum of R of n to the, I'm going to find a point, say n to the power minus half, s is equal to half, going from n going from 1 to infinity. This is greater than or equal to sum of, this was the n square I found, remember? R of n square. So R of n square greater than n. This is always greater than or equal to 1, as we showed. And this is greater than or equal to sum of 1 by n, which, if we have studied, we know that this is a divergent series and this is equal to infinity. And that cannot happen. So Rn n power s cannot converge and diverge. So conclusion is L1 chi is not 0. Okay. So in both cases, L1 chi is not 0, whether chi is quadratic or complex. Are you completely convinced with this? According to the program that was written out, I was supposed to do Siegel zeros today, but we'll do that next time, because we also should have seen this program.